Last time we learned about MOSFET and IDVD Characteristic. So this time we are going to learn about threshold voltage and MOSFET structure. First, last time we learned about the MOSFET first state. First version is flat band condition and accumulation and inversion and depletion mode. We learned first state. So in this threshold voltage, it is related to inversion mode. So last time we drew the IDVD characteristic, and we also learned about the condition about the inversion mode. So when the inversion mode started, the substrate voltage is 2 phi B, and 2 phi B means intrinsic Fermi level minus Fermi level. So as the result, we also can define that the threshold voltage is flat band voltage plus oxide voltage plus 2 phi B. And we can define this oxide voltage like this. But in threshold voltage state, the phi S is same to 2 phi B. So as the result, the sum voltage is flat band voltage plus Cox by 4 sine Q and donor concentration and phi B plus 2 phi B. So this is the equation of threshold voltage. But be aware that this and this polarity when we use the N-type substrate from the MOSFET, N-type substrate, the polarity is inversed. So when we calculate it, we consider that the oxide and substrate voltage are minus. So that is the threshold voltage. And now we will see the MOSFET and MOSFET structure. MOSFET has three parts: gate and source and drain. So when we use the N-type heavily doped source and drain, we can call this MOSFET. When we use heavily doped P-type semiconductor in source and drain. We can call this PFET. And usually when we make a MOSFET device, we usually use P-type substrate. And for PFET case, we usually use N-type substrate. And when the MOSFET state, the channel has made it, the majority carrier is electron, because we used heavily doped N-type semiconductor in source and drain. And in the same, in PFET, when the channel made it, the majority carrier is hole, because also we used heavily doped P-type semiconductor in source and drain. So we can draw this small lake in like this, and this part is source and this part are drain. And if we by using this device, we will give some bias to gate and between drain and source. So if we give a bias to drain and source, the drain level goes down like this. And the flow occurs like this. That is how to MOSFET device the current is occurred. But when the drain bias goes up and up, this flow stopped like this. So we can call this situation the pinch off. So by this phenomenon, we can explain it by using the IDVD characteristic. When the drain bias occurs, the current goes up like this. But when the drain bias goes up higher, the pinch off occurs, and when the drain bias goes up and up, even the drain bias voltage is higher, the current doesn't go higher. So that saturation point exists. So we can draw IDVD characteristic like this, and the gate voltage goes higher, we can draw IDVD characteristic like this. And the gate voltage goes down, the IDVD characteristic draws like this. And we can draw the ID and gate bias characteristic. Last time we learned about that the CV characteristic, CV, and we can draw the CV characteristic like this. And this is accumulation mode. And these regions are depletion mode. And these regions are weak inversion. And when the voltage gives more than threshold voltage, after this part are strong inversion. And so let's see this part. When we integral this part, we can draw this part are constant, so if we integral this part, we can draw this part like this constant function. So we can draw the IDVG characteristic like this. When the gate bias is less than the summer voltage, the drain current flows approximately 0. But if the gate bias is higher than the summer voltage, the drain bias goes up like this constantly. So this is the IDVG characteristic. So the fourth topic is carrier transport. So we will draw the MOSFET band diagram. So I draw like source, channel, drain band diagram, and it's a thermal equilibrium state. And this is a MOSFET because the source or drain are heavily doped N-type, and by this part you can see the built-in potential. This is a thermal equilibrium state, and when we give a gate bias from this MOSFET, we can draw this band diagram like this. The built-in potential between source and channel to drain are more lower. So there has a lot of electron carriers here, and by giving the gate voltage, a lot of carrier can go by source to channel. And when we give a drain bias from here, it can make a drift current from here. So this electron carriers flow like this from drain. So the drain current exist. So there are two modes in the MOSFET. The first mode is enhancement mode and second is depletion mode. Let's draw a IDVG characteristic again from an MOSFET. We can draw IDVG characteristic like this. And this point is threshold voltage. But when we don't give a gate bias, so it means the gate bias is 0 voltage. Even if this state by the flat band voltage is too big from minus in MOSFET, even if the gate bias is 0, but the channel is already occurred like this. So it means even if we don't give a gate bias from this device, but already channel is occurred and current flows like this. And as a result, the threshold voltage is minus from MOSFET. So we can call this depletion mode. And let's see this characteristic again. When the gate bias is 0 volt, like here, it doesn't have a current flow. We can call this mode enhancement mode. So from when the pivot case, we can draw the IDVD characteristic like this. This is IDVD. We can draw like this. This part is pinch off, and we can draw like this or this, depend on the gate bias. And by this, we can draw the IDVG characteristic in pivot like this. and this point are summer voltage, and this mode is enhancement mode. Because when the gate voltage is 0 volt, there has no current from here, so it means the channel doesn't made it. But when the summer voltage is plus from this PFAS state, the IDVG characteristic draws like this. So even if the gate voltage is 0 volt, the current exists and the channel has made it. So in this type, we can call this mode depletion mode. So as the conclusion, even if we gave a voltage, a gate bias is 0, but the channel occurs, we can call this depletion mode. And if we give a 0 volt in from a gate bias, and if the channel doesn't occur and the current also don't flow, we can call this mode an enhancement mode. So this time we learned about threshold voltage when the inversion occurs, and we also learned MOSFET structure and IDVG characteristic, and we also draw the Venn diagram of MOSFET. And after that, we learned about enhancement mode and depletion mode.